Thank you so much. At the outset, thank you to Atal FDP scheme, Amrita Viswavidyapitam, and all the participants for letting us share our thoughts and views on the architectures for supercomputing. It was nice to hear from Professor Arun Kumar about one of the key applications that are relevant to India as well. Agriculture and supercomputing, how they can help each other. It's really indeed a very relevant topic for our country. And today, what we would like to do is we have Ms. Deepika, who is really an expert, and she has seen the world, how things have evolved over the last 2+ decades in this particular area of various architectures. But before she starts, maybe I'll give uh, maybe a slightly higher level view of where we are headed to as a country. So supercomputing today technically is no more a buzzword. It is something that is very grounded, and in fact, you can say the edge computing or the smartphone that you carry in that class are more or less like a supercomputer, in the sense you've got multiple cores and they have enough memory and they have the ability to kind of form an ad hoc network through various technologies to work together as a cluster. So from that perspective, we can look at supercomputing as an area where we combine, where the 1 plus 1 is not equal to 2, but it could be 11 or more. So that is how we are looking at supercomputing, where multiple cores join hands together and the memory is shared in an appropriate way and communicated so that they perform together at a speed of more than what the linear combination is. Um, in fact, we should beat the Amadal law by utilizing the synergy, by appropriately utilizing the memory and the way it is shared, and some heuristics and other algorithms that are possible to achieve superlinear scales. And that is also made possible with the emerging architectures, where we are combining like a GPU, CPU, uh, accelerators of different type, whether it is crypto, whether it is language model, or whether it is AI accelerator, or it is some image enhancing or image processing accelerator or coprocessor. Those kind of things can actually make sure that each one is optimized for a specific activity, and together they ensure global optimal optimization. That is what we are looking at when we talk about these kind of architectures. And most of the architectures, I think there was a question before in front of Professor Arun Kumar, that what makes a supercomputing type of problem. So if at a high level we can cluster them into 2-3 activities. One could be where the computation can become high fidelity, or they can become micro granular as we go more and more deeper. So basically the fidelity keeps increasing. So that is one kind of place, we can look at supercomputing as a basic requirement. A classic use case could be weather forecasting, where the grid size for which we are forecasting the weather comes from, from multiple square kilometers to square kilometer to square meters. That is one thing. The second applications could be where identical computing but humongous amount of data. For example, our a good example could be our UPI, where lakhs and lakhs of people use every second, and it's all computing the hash, computing the digital signature, whatever the algorithm it is for signing purpose, digital transaction. So it is the sheer volume of data with a well-known repeatable compute part or processing part. Then we have got a third type where it is a kind of a compute, communicate, and synchronize, which is a kind of a grid computing, that kind of things. That is also a supercomputing problem. where one use case could be, the way you do matrix multiplication. You break down everything into a 2 by 2 matrix, and then, combine them together. A kind of nested loop kind of thing happens. So how large two matrices could be for multiplication purpose? That is another kind of compute. So we can bucket them in different ways, and each type of problem performs better in a particular type of architecture. So the optimization of the multi-constrained way is going to change. That is how we are looking at it. And as a country, we have done a lot under National Supercomputing Mission, and CDAC has been working in this for the last 35 plus years. And system software has been developed by CDAC Bangalore for a long, long time. And that is the reason we believe we'll be able to share some of our experiences on various architectures we have tried in the past and what we are currently trying and what is coming up. So that may give a glimpse for most of you to take things forward at the end of the session. So without much ado, I don't want to take the thunder away from Deepika madam. So you can take over from now, and you can walk through the formal presentation, madam. And towards the end, hopefully, if there are some questions that we could answer, we'll answer together. Thank you so much. Yeah.
Thank you, sir. I'll just share my screen. Hopefully my window is viewable.
Yes, ma'am.
Even my audio is clear, right?
Yeah.
Okay. Thank you for inviting us. And today's session will be talking on deep dive into supercomputing in terms of architecture, parallel processing, and the real impact in terms of use cases, what you see. What actually in the previous session also I heard, what are the use cases? So maybe we could give you some bit of glimpse, and already sir has given you an understanding of how you can put in different buckets and you can view into as a different domains. Over and above, if something else, some of the other examples what we see currently, what we are supporting, those things I would like to put as the use cases. So the outline of my talk is going to be, first of all, to understand what is the supercomputing, what is high performance computing. More of we find when we go for any sessions, they're used as jargons rather than understanding what is the difference, or are they one and the same, or what is parallel computing. These words are just used around without understanding the exact meaning or for what they are used. So first we'll try to figure out these things, and then we move on to the architectures. We have the top supercomputers of the world and as well as India, and some of the major breakthrough in architectures which has led to today's supercomputing in terms of CPUs, accelerators, and where are we going way towards the next road ahead, not only in terms of the world as well as in terms of our Indian supercomputers. Then we move on to the parallel processing or parallel computing, and some of the models, how are you going to write programs, just a glimpse of it, how you can use, what are the paradigms you can use, and then we'll close it out with the use cases. So this is what I have planned for next 1.5 hours. So starting with, when you say supercomputers, these are the machines which come into everyone's picture, right? So this is a picture of the the fastest supercomputer in the world, called as El Capitan. It is in United States of America, and it gives around 2 exaflops. Exa in the sense 10 to the power of 18 floating point operations, okay, per second. This is the kind of computation what this particular machine can do as a whole. And now if we are talking of this at the world, what is that we have in India? In India, we have the fastest supercomputer called as Airavat, which gives something called as 13 petaflops. Peta in the sense 10 to the power of 15 floating point operations per second. This is the amount of floating point operations that it can crunch in a second. And this is the fastest supercomputer currently what we have within India. So next, if these are your supercomputers, they look beautiful, right? They have a very nice way of putting across in the big cabinets and making it look good, like your supercars, like your Ferraris and all. They have a very good look and feel. But so what is this supercomputer? What are these boxes, or what is that they do? Right? So supercomputer, you can say it as a form of high performance computing that uses supercomputer to reduce the overall time to the solution. That means we use these supercomputers. These are the infrastructures or the hardware what we use to solve certain solutions. Okay. And why do we say it is a form of high performance computing? Supercomputing or supercomputers make a part of the domain called high performance computing. Okay, the whole domain, you can call it as high performance computing. Under that, one of the most successful and fastest kind of a machine what we use for achieving, or what we use in this high performance computing domain, is called the supercomputer. And working along with it, you can say it as a supercomputing, right? So what is this high performance computing? If you're saying supercomputing as a form of high performance computing, let's say, rather than going by definitions, it's a way to combine the best possible compute power along with the parallel computing techniques. When you have a hardware, you need to have a supporting software for it. So what is this software so special about it? It's all about the parallel computing techniques, what the software encompasses in it. And using this hardware and software, that is the best possible compute power with the best possible parallel computing technique, how do you solve complex computational problems which you cannot solve, or which you can say that it takes days or months to run on your simple laptop or even on a single server or workstations? What cannot be solved here, which can be rather because of your memory, it cannot be even executed, or if it is executed, it's going to take a very long time, then such kind of problems or applications can be put on these supercomputers, and then you can run it at a at a very faster time and reduce the total solution time for getting the solution. So this is all, or this is what you need to know about what is supercomputing, what is this high performance computing. And when we say high performance computing, I said supercomputers are one of its kind of the infrastructure, right? Why? This is Paramutkarsh. This is the facility which is at CDAC Bangalore, which is currently existing and which is working on under NSM. So what is this supercomputer? It's a tightly coupled computers which work together, giving the feel of a single computer. If any of you have used the supercomputers, what you do, you log into a particular IP or a machine, right? That's your home directory. From there, you submit your jobs, and then these jobs are run on many n number of servers. Each of these racks, right? They'll have some 16 to 32 blade servers, we call, okay, housed in each of these racks. So they run across these n number of servers, and then the result is accumulated back and it's given to you back onto your home directory. And what is the picture as a user you get? It is like you've just computed on a single computer. You do not realize as a user that it's running across n number of different systems, right? So that is a speciality of a supercomputer, where it's tightly coupled together, which gives a picture of a single computer. So what are the other infrastructures what that HPC uses? You can say the most simplest is the distributed computing. Even your lab computers, right? What you put together with a network switch, that can be the basic form of distributed computing, where you have different systems sitting, but they all are connected through the network, right? Which are communicated over the network, and you can run a program by distributing it into certain parts and run it on those systems and get back the results. Or the grid computing is you can say the bigger form of a distributed computing. Here it's not only existing, or grid computing doesn't work on a single place, whereas when you say supercomputer, this whole supercomputer is existing in a single place. Whereas when you say grid computing, these are geographically available at different places, places, okay, different locations. You combine these different kinds of servers, even a desktop CPU cycles can be used, different kinds of instruments like your satellite terminals or your telescopes. So all the instruments, any kind of computational instrument or compute node or a server can be added to the grid and can be used together, right? So this is more of an aggregation and sharing of this heterogeneous kinds of instruments or systems. Then last, this is something what we all know, right? The cloud computing, because it's an on-demand service and you pay it as you use and and it's accessible over the internet, right? You just log into one of your cloud computing service like your AWS or Microsoft Azure, and you start once you use, or when you say, okay, I want this particular container or this particular VM, you own that particular VM and you start using it, and but you pay it for only the use, right? And again, for what you pay, either for infrastructure as a service or as a platform as a service or as a software as a service, right? So these are the different kinds of infrastructure what HPC supports, the domain of HPC uses. But among them, supercomputers are the best and the fastest medium or the infrastructure to get the solutions faster. And for very large programs or problems to be solved, then supercomputers works the best. So if that is the case, I have said already that they are tightly coupled computers. So what is that makes it special or better than the other infrastructures what we talked of, right? So it is the practice of aggregating the best possible compute power to deliver the superior performance as opposed to your other infrastructures like your distributed computing infrastructure. Grid can have multiple supercomputers also, but in general it will have even your other instruments, right? So they are not very concentrated on getting your solution working on a single place. So, and cloud computing, exactly, you own a system, but you're not particular about the time or the fast pace in which the solution can be got, right? So, what is supercomputer? What are we trying to achieve? Yes, ma'am. One of you had a question. They have raised their hands. Shall I continue?
They can talk now. The participants, if you want to interact, those who are raised hands, please interact.
Or else let me take some breaks in between, like once I complete a particular set of things, shall I take it up? Or yes, the one of the hands are raised, I can take up the question.
I think they mistakenly did, it seems. Okay.
It's okay, fine.
Okay.
So what is this? So what are we doing with supercomputers to be the fastest? We aggregate the best possible computing power to deliver the superior performance. So when we say we are aggregating the best possible computing power, it is about working from the lowest level technologies, right from the circuit design, right, to get the best possible performance out of that compute power. So, and how do you utilize these components, what you have developed, to get the best performance, and how do you deploy it or employ it into your supercomputers to make it run faster? So that is what is special about supercomputers. So that's how it works. Now, this is the backplane, we can say, of a supercomputer. Like these are known as racks. Inside the racks, you have multiple servers. They are stacked one upon the other, okay? And they are connected across. If you see, there are some wires, right? They are connected across with wires so that they can pass on images across different servers. There are different topologies with which you work. So right from when you say the lowest level technology, right from your chip to your motherboard, how they are connecting to the other different parts of the peripheral devices, to that makes your compute power, let's say. And how do you enhance parallelism at the hardware level? And then how are you going to connect these servers across to give the lowest possible latency when you're running a program? And together, how they will work to get the best performance as a solution. And here, when you're running across these different servers, right? When you look at the backplane, different servers, they are going to execute separately. They have to be aggregated back again into a single place where you have submitted a job, or the master node, what we say, and then you get back your results, right? So now when we are saying these are the things what we need, what in a supercomputer they work on. So let's look into, before saying, okay, the top supercomputers, what is the history or what we see in the world? Like, where did this whole phenomena of supercomputers started? It all started in 1961 with the IBM 7030, which was working. And this is a picture of what I could find about that particular system, which was running fastest at that time with 1.2 million instructions per second. And that is when they came up with the next machine called as CDC 6600. Okay, this is the first. And before this particular machine came up, they wanted to figure out what would be the metric to call it as a supercomputer. So that is when they arrived that we won't be going with the instructions per second or million instructions per second. Rather than, let's go with the metric of flops, that is floating point operations per second. How many number of floating point operations per second can this particular system crunch? Based on that, the fastest system can be pointed out, right? So in 1964, this was the fastest system. In fact, this is considered as the first fastest system, and it was developed by Seymour Cray. In fact, that's a reason he is known as the father of supercomputers. And it was able to give a performance of 6 M flops. That is, M stands for 10 to the power of 6. Okay, 6 in multiplied by 10 to the power of 6 floating point operations per second. So further, he came out from CDC and then he established his own company called the Cray Systems, and in which the other systems of Cray, or the first system of Cray Systems was started. And this is how the Cray Systems look. They not only worked on how can the fastest machine work, but they even worked on how the fastest machine should look. So that's where when you saw the first slide, right, you had a beautiful picture of El Capitan and a beautiful rack of Airavat, right? And Airavat is currently housed in CDAC Pune. So what was this in 1970, the first Cray system called as Cray 1 was brought in. So what was new about this particular computer? Why was this called as a supercomputer? Not only because it gave something called as 160 M flops, that is mega flops. It was the first system to start working on something called as a parallel architecture. Till then, the concept was simple, like your von Neumann architecture, where you had a CPU and your rest of the things. But this was the first machine which was able to do vector processing. So vector processing was the first kind of, and you can say, a step forward in the supercomputers which was brought in, which made it work faster to get this 160 M flops, which continued to the Cray 2 system. But the additional feature what they added was adding a processor which was liquid cooled. Okay, giving it a performance of 1.9 gigaflops. Now you see, from M 10 to the power of 6, we have moved to gigaflops, that is 10 to the power of 9 floating point operations per second. So this was the speed at which these systems were working. Further on, in 1996, similarly, Intel came in. They had a series of ASCII machines called as ASCII Red, ASCII White. So they brought in with different kinds of supercomputers. And their first machine among that series was this ASCII Red, which gave a performance of 1.3 teraflops. Tera means 10 to the power of 12, right? So these are the metrics I would like you to remember, because I'll be using these M flops, gigaflops, teraflops, petaflops further. So when I say megaflops or MF, so it is 10 to the power of 6 floating point operations per second. If we say gigaflops, that is 10 to the power of 9 floating point operations per second. Teraflops would be 10 to the power of 12 floating point operations per second. Petaflops is where the current Indian computing power are lays, right? That is 10 to the power of 15 floating point operations per second. And in the world, we have currently 3 exaflop machines, okay? The rest of the machines are still in the floating point operations, or we can call it as petaflop machines. But there are 3 machines, which are the top 3 machines of the world, which are exaflop machines, which are able to work at the speed of 10 to the power of 18 floating point operations per second can be calculated, right? So these are known as exaflop machines. You can get this top 500 list, right? It is announced twice a year, once in May or June and once in November. They have 2 conferences called ISC, which happens in May or June, and there is a supercomputing conference which happens somewhere in November, where these fastest supercomputers of the world, the top 500 list is released. So the latest has been the last November list. These are the systems what we find as the top 5 world's fastest supercomputers. If you look at it, they're, as I said, these are the first 3 systems which are working at exaflop, right? That is, when you say it is 2746 petaflop, p flop means peta, 10 to the power of 15 floating point operations per second. That exa is divided by 1000, right? So it becomes so it becomes exaflop 10 to the power of 18. So it becomes 2.7 exaflop, right? So the first 3 machines, the fastest first 3 machines, what we find, they are working at the speed or the max speed or the peak speed what they have ever achieved is 2.7 exaflop. That is your L capital. Then there's a second machine called as Frontier. It has achieved around 2 exaflop. And the third machine is called as Aurora. That is 1.9 exaflop. Okay, if you look, there's a huge difference between the third and fourth, right? From 1.9 exaflop or 1980 petaflops to the fourth machine performance is 846. From there on, if you look at it, the rest of the next machines, what are there till 500, they all are in petaflops. In fact, I think the last within 500 you will find machines which are capable of something like 3 petaflop or 4 petaflops. And what is the other thing what you observe is the systems. They are the top 2 machines are from AMD, right? The CPU used is the AMD's Gen Epic systems. Then the third system uses Intel's Blade or the Xeon machine. And the fourth supercomputer again uses Intel's Xeon machine CPUs. And the fifth one uses AMD. So basically it is more ruled over with your AMD CPUs and your Intel CPUs. Other than this, there are few systems which uses ARM-based servers, like the top 6, the 6th supercomputer, which is known as Fugaku from Japan, that uses ARM CPUs. Okay, and other than this, what is that you observe? You can observe the GPUs which are associated with it, right? So for this AMD machine, they have used the AMD GPU itself, that is MI300A. And then for the Frontier, they have used MI250X. And for Aurora, they have used Intel's Intel Data Center GPU Max, okay, or what we call it as Ponte Vecchio. Then the fourth machine, Eagle, uses NVIDIA H100. And the fifth machine again uses AMD's GPU, that is MI250X. Further on, if you again observe, there are basically, other than this Aurora, there are no other machines which has Intel GPUs. So it's basically this whole 500 list has either the AMD GPUs or the NVIDIA GPUs. So these are the accelerators what you find in the supercomputers, and these are the CPUs or the make of the CPUs what you find currently. Okay, along with it, when we see here, most of them are using something called as slingshot. This is the interconnect used, and if you observe, all machines are Cray machines. The first fastest supercomputer, which was developed right in 1970s, the Cray systems. It is the same company which has went on to till now give the best fastest supercomputers. Obviously, Cray was sold out to HP, so now it is called as HP Cray Systems. And what is the other thing what you observe? The number of cores it utilizes, right? Somewhere around 11 million, 9, right? And what is the other thing which is very stark and you can actually say is most of them other than the fifth machine all belong to USA, right? And your fifth machine belongs to Italy and the sixth machine belongs to Japan. So what is the other thing what you can look at it now? If you observe all these top 3-4 machines, or in fact in the top 500 machines, all the machines which have been, most of the machines, let me not say all, when we look at Eagle, we are not sure whether it is funded by United States government or not, but most of these systems are supported by their respective governments. The reason is building a supercomputer takes in a huge set of money, as well as maintaining and operating that also has a huge cost involved. So it works out better for getting or running these supercomputers along with the support of those particular governments. So most of these supercomputers are funded by their respective government organizations. Then so what is that? Where is that India stands in all this supercomputers? We have few supercomputers in the top 500. We'll talk about it. So where did our journey start? The world's journey started in 1961, but where did our journey start? We used to buy these supercomputers, these Cray machines, until 1988. Okay. And only in 1988, when this particular supercomputer was trying to be, we were trying to purchase, there was a denial of the supercomputer to be bought or to be purchased by India. And it was supposed to be purchased for doing a weather forecasting kind of a work. And since it was denied, then our then Prime Minister, uh, Shri Rajiv Gandhi ji, had decided if we cannot purchase, we'll build our own supercomputer. That's how our organization CDAC, Center for Development of Advanced Computing, came into existence in 1988. So we have been working on this series of computers, what are named as Param series of supercomputers since then till now. And this is one of some of the major achievements or some of the major systems what you find from 1991. The first system, 1988 was when CDAC was formed or CDAC was established, and a first system what started getting not only built, but we even exported to something like 14 such systems were built and exported to outside our country. Okay, so that is where our journey as Indian journey of supercomputers started with Param 8000. And there's a very interesting story what our first director Vijay P. Bhatkar sir mentions, like how did, based on what questions. It's a very famous interview also, you'll find these articles, where he mentions that he was asked 3 questions based on which the organization was formed. The questions were simple. How much time will you take to make a supercomputer? What would be the cost? And by when, or first question was, have you ever built a supercomputer? For which he mentions in the article that no, we have not built a supercomputer till now, but we can build it. And the second question was, how long will it take? And he mentions that he's answered like as much time as it would take to buy or purchase that particular Cray machine and get it to India. It used to take 3 years after getting an order to bring it back to India. Okay. And what is the cost at which we can build? The then Cray systems were supposed to be bought at a cost of $10 million. And he had said, okay, we can make that system within the same amount at which you are purchasing. So that's how with these three, with the confidence on the founder director and his team, CDAC was formed. And in 1991, this Param 8000 was built, and it was not only just one of the machines in the foray of other world computers. In 1991, there was no the supercomputing list. Okay, they had to take these machines to the supercomputing fair. In 1991, it happened in Zurich, where they took this particular Param 8000, assembled it there, and they ran, and it turned out to be the world's second fastest system. The first system what India built was the second fastest supercomputer of that time. So that was the power of the Param supercomputer, or rather, let's say that's the power of the Indian journey where the supercomputer started. We not only made it for ourselves, we even sold 14 such machines. And can you guess at what cost was it sold? It was sold at 1/3 of the cost at which Cray was. Cray was selling it around $10 million. And now Param 8000 was sold at something like $350,000. Not 10 million, $350,000. So this is what was claimed. So this is a small story of how the journey of CDAC or journey of Indian supercomputers started. So if you look at our journey, which was this Param 8000 worked at 1 gigaflop, right? Then the second machine was called Param 9000, which gave a performance of 2 gigaflop. Then the third system was called as Param 10,000. Again, this was something like 6.4 gigaflops. Okay, so 2 gigaflops was 9,000, and 10,000 was able to perform at 6.4 gigaflops. Then came the first teraflop machine in year 2002, which was housed in Bangalore. These three initial systems were housed in Pune, and this was a machine which was housed in Bangalore center of CDAC called as Param Padma, and it clocked around 1 teraflop, that is 10 to the power of 12, right? Then came the other machines like the Param Yuva with 54 teraflops. Then we had some special machines which were very specific for biology. Okay, they were called as Param Biogene or Param Biochrome. Then we had if you look at these set of machines, like the three machines, these are very specific to the biology domain machines. Then we had our other generic machines like Param Yuva was upgraded to Param Yuva 2. That gave a performance of 529 teraflops. Then we further went on, and when we look at it, we built the first supercomputer called as supercomputer in a box. That is, this is a simple box, okay, like your servers, but the performance is equivalent to a supercomputer. That's the reason it's called as supercomputing in a box, and that's named as Param Shavak. And it gave the performance. The single box was able to give 18 teraflops. This was placed, the order was placed at, or it was placed in 25 places. And this was started in the year 2017. And till date, we do sell all this Param Shavaks across different engineering colleges. Okay. And then in 2017, we started our current National Supercomputing Mission, NSM, where now we have installed 25 supercomputers across different institutions. Let me make this clear. It's not just there in CDAC Pune or CDAC Bangalore. We have these machines in all your IITs, NITs, and most of your educational institutes. Okay, so there are somewhere around 16 to 18 installations, and some of them are private and very specific to certain problem solving. So the journey started for NSM with the first installation of 833 teraflop speed machine called as Param Shivai, which was inaugurated by our current PM Narendra Modi ji. And from then on, we have installed around 14 to 18 systems, which make something like 25 petaflops. 25 to 30 petaflops is the amount of compute power which has been installed across. Now the thing, when you look at the worldwide, we say we are talking of exaflop, we are talking of something like 800 petaflops, and in India, we are talking of something like 30 petaflops, right? So what is great about it? It is not concentrated in one particular place. Like the question what I heard in the previous session, most of us, we are in the same state. What are the kind of applications that we can run on these machines? If that is the case, having a huge one exact flop machine currently won't make a necessity or won't make any sense to India, right? Rather have multiple petaflop systems across on different parts of India so that it's accessible to all the institutes. And these NSM systems are accessible to all the institutes and all the people who want to work or research on it. And can you guess the price? We charge somewhere around like 0.90 paisa per hour for the CPUs and somewhere around 40 to 49 rupees per hour for the GPU. So it's very affordable and it is available for all the users. It is not restricted to particular organizations, but it is open to all and to all the researchers who want to work or utilize the supercomputers. And that's the reason it was installed across different NITs, IITs. These were the places or campuses what were identified in our NSM. And the fastest supercomputer among all these currently is our Param Airavat, which gives a performance of 200 AI petaflops. Okay, or rather, let's say in terms of just floating point operations, it gives 13 petaflops for the HPC. Okay. What are the top 5 machines? What we find, you can find these top 5 machines like the top world top 500 machines. India also maintains a list which is updated twice in a year, once in January and once somewhere in December. And you can find this list in this particular URL, topsccdacb.in, and it's maintained by CDAC Bangalore. And the top one ranked machine is called as Airavat, as I mentioned, and it's housed in Pune. And the second fastest machine is your Pratyush, which is from IITM Pune. The third machine is called as Mihir, and it is housed in NCMRFW Noida. Fourth is the Param Pravega, which is housed in ISC Bangalore. And the fifth machine is something quite special to CDAC, and I think something what as in India also as a way forward towards a supercomputer also what we find this as special. And because this was an indigenously built server called the Param Rudra, and it's placed in Ayuka, Delhi. So if you look at it, what are the systems or the chips or the processors what we are using currently in our top machines? These are again the AMD machines or the Intel CPUs, right? And if you observe, most of them use NVIDIA GPUs, right? All of these machines have NVIDIA GPUs, like your top fourth machine or the top one machine. In fact, your Pratyush and Mihir are totally only CPU based machines or clusters. And then you have the last Param Rudra, which is a combination of Intel CPUs and the NVIDIA Tesla A100 GPUs. And what is the best performance what we can get from Airavat? It is 13 petaflops, or we can say 13,000 teraflops, right? And then for Pratyush, we can get around 4.6 petaflop, and from here 2.8 petaflop, and from Pravega 2.5 petaflop, and from Param Rudra we get the best or the peak what we have achieved is with 1.8 petaflops. Accordingly, the number of cores used for these petaflops are also respective to that, right? And so where in the world ranking these systems are? The first system what we have Airavat, it world ranking is 136, and the second Pratyush has a world ranking of 268, and Mihir has a world ranking of 431. So Param Pravega and Param Rudra are beyond 500, so they are not listed among them. Any doubts till now, or do we move on to the architecture?
Participants, you have any queries, you can raise your hand now.
Okay, we'll move on to the architecture. on to the processor architectures now. We talked about the overall. Yes, Rajendra Kumarji. I find a hand raised. Do you have a question?
Sir, you can talk now. Actually, you are not audible. I think you are using earphone.
Or else you can write it on, if chat is enabled, you can write it on the chat. Later on, maybe once in a while, okay. If something is there, I can ask. Okay, there was a question. Are we exporting supercomputers? Why can't give it to educational institutes? It can be given, sir. But let me tell you what is the problem with this. It's not about just building a supercomputer. It's about the operational cost. The main thing is the power bill. Power bill or the operation cost is too high to maintain. And these supercomputers, actually, many institutes have set it up. And what is the feedback we got? Let me be very, I don't know, realistic. We have heard of certain, I do not want to take certain the names of the institutes, but they were very of the HPC cluster in their institute. They set it up, and once the actual system administrator or the HOD involved, they left the institute, those systems were shut down. So there was no plan of how is the TOT or how they are supported. It is not that it won't be given. Yes, they can be bought. How can we make use of supercomputers for research and how to get that to our institute? So you can always access these NSM systems which are already available. The reason why I'm saying is maintaining or the administrative level of confidence what you require to maintain such huge clusters there, or that kind of difficult. Then rather than like the way you use the cloud, you want to, whenever you use it, you pay for. Why can't you use the existing facilities when these facilities are available for anybody to log in and to pay and use? I think that makes a lot sense. In case you still want to own it, say first start out with Shavak, right? The supercomputer in a box. Once you flood your application and your data, you exhaust it with that supercomputers, then you can move on to the bigger supercomputers and working. So this is something what we are looking at, or we would say, we would suggest to go around with. CDAC supercomputers, are they made fully designed? The Param Rudra we have taken, okay. Again, this is the path of self-reliance. Though our first supercomputer was built with our transputer own things, somewhere down the lane, we have been just assembling the boxes. But Param Rudra, what I mentioned, the current top 5 supercomputer of India, where we have just taken the motherboard or the chip or the Intel chip, and the whole server has been built by us. Servers are not just your processor, right? You have multiple other things involved. So the whole server is built by us, and that is Paramrudra. And yes, that is the first step towards self-reliance. And the second step is we bought out a design, and then we are building our own chip and then the whole supercomputer. And the third and the final step, what we are looking at, building the even are not get your own design, have your own design rather than buying a design. So this is the way ahead for our self-reliance. So yes, we are going step by step back again. So when we say currently, is it fully designed? The server is completely fully designed in India, but the motherboard is what we have bought. That's the Intel motherboards or the AMD motherboards is what we have bought, and around it, the whole server has been designed within CDAC. Any other questions? Okay, let me continue back. So we all know that all your CPUs or computers, they started with the one human architecture, right? Having a CPU with some ALU and CU, the control unit, having a memory attached to it and input and output. Is it that changed today? No. The basic one human architecture currently also is the same, right? Just the way it has had multiple CPUs or added some more new features has made it faster, right? Like what are the features, like adding caches to your memory to make it to give a better, faster access, or the speed of the CPUs has been increased, and adding the coprocessor or accelerators, which has been a very huge change or a break into our computing facility, we can say. So if we look at it, until like you saw the Cray 1 system, right, 1970s, until then they were all single CPU machines. But Cray 1 was the first machine which brought in the parallel architecture into the hardware. So what was it? The parallelization, what it brought in, it was able to, it is called as a vector processor. It was able to run mathematical operations on multiple data simultaneously. Till then, it was one instruction per one clock cycle, right? So it was able to crunch in within that clock cycle multiple data elements at the same time within that clock cycle. So that's known as your vector processor. Then further on, this continued to, let's say this was in the 1970s to the late 1980s. Then the superscalar processors came in, where the instruction level parallelism was taken care of in a processor. And what were these machines? These were the Intel 960 Sun Spark machines, or MIPS R, or the AMD's AM29000. These were the instruction level parallelism, what was taken care on, rather they were known as a superscalar processors. Now, after this, it led to only in the early 2000s, we came across with multi-core machines. I guess most of you professors have started out your career or mid of your career, you've all come across using this Intel Core 2 Duo processor, right? These were the first kind of machines where instead of having a single CPU in your chip, we had two CPUs, right? Till then, it was always a single CPU, like your one human architecture. But only in your early 2000s, that's when they brought in this multi-core machine, the concept of having multiple cores into a machine, or rather, let's say, having two cores into a machine. Okay. And then they found, okay, what is the next level of enhancing these systems? That was, you have multiple such multi-core machines. So these were known as multi-chip modules, okay, like your power forward machines. They had this multiple two-core CPUs, and even today we use this concept, right? Where we say a two-socket machine or a four-socket machine or a two-way SMP, right? So two-way or two-socket. So these are the sockets, what is there, right? And each socket will have its own multi-core machine, right? So this has continued to expand, which started with only two CPUs in one socket and having multiple such socket as an extension, okay? To today's symmetric multiprocessors, which house something like each of the socket will have something like 24 to, let's say, something like 56 or 64 cores in one socket, right? So how are these machines working? These are known as the current machines, what we see in India, the Skylake, Intel Skylake, or most of our supercomputers, or most of the world's, let's say, some of the machines of the world, most of them currently which are existing or which are being used, they are the symmetric multiprocessor, where you have a huge single shared memory, and to this shared memory you have multiple CPUs attached, and each CPU will have their own cache, okay? And how many such CPUs can be put in one socket? It varies from 24 to 56 CPUs per socket. So in our machines, what you see, right, in the Param series of machines, what we are having currently in India, you'll have a two socket, that is, two such CPUs will be there in one node or a server, okay? So you'll have, let's say, our Paramutkarsh, you have something like 24 CPUs in one socket, and since it's a dual socket or two socket machine, they'll have two such CPUs, making it 48 cores per node. Okay, and per node or per server, blade server, what we say. And multiple such servers are stacked one upon the other in a rack or multiple such racks, making it a supercomputer. So now, if this is where we stand with symmetric multiprocessor, where are we going further? Way ahead is called something called as an disaggregated system on chip, or SOC machines, right? Where instead of having a single die do all the work or have all the cores in that particular machine, rather we have smaller chips, right? And they're called as chiplets. And these chiplets are stitched together, and they are interconnected using the protocol called Universal Chiplet Interconnect, that is a UCIe. And these are some of the latest machines, what you can see. The top three machines are using AMD Genoa, this architecture. And there are some machines which are being built yet using Intel Sapphire Rapid or the ARM V2 CPUs, which use this technology of disaggregated system on chip. So let's talk about the Intel Sapphire Rapid. So till your previous or the current machines, what we are using in India, right? They are like this monolithic single dies. So instead of this single die, they are having small 4 cores or chiplets, what we call, okay? 4 chiplets are put together to form the complete die. And this 4 chiplets together form a package of 60 cores. And here in Intel, what is that specific, what they have done with the 60 cores? They have connected these 4 chiplets having something like 60 cores together through a mesh topology. This is how it will look. You have 4 chiplets, right? 16 cores in each it should be, right? But that would make it 64 cores. But in each of this chiplet, one of the space or the one of the mesh is, instead of having the actual CPU core, you have a memory controller. Okay, so in those 4 chips, each one place or of that particular mesh is removed out with the core, and rather you're having a connector for the memory, thus making it 60 cores and not 64. Okay, and this is how the latest or Intel machines will come up with the Intel CPUs called Sapphire Rapid. Fine. And what is the equivalent? What we see in AMD is also same, where you have chiplets of 12 chiplets. If you see, instead of 4 chiplets of Intel, AMD has gone further with 12 chiplets, and each chiplet housing 8 cores or 8 CPUs in each. And in Intel, if you see here, it's a mesh, right? Mesh is the way these CPUs are connected. Whereas in your AMD Genoa, they use the bidirectional ring bus topology. Okay, a ring topology is there for connecting all these cores across through the IO device. So this is the latest or the future CPUs, or the way ahead for the CPUs, what we see or look at it using the chiplet design, where we find, okay, they will continue to have more number of chiplets together, each chiplet with some n number of cores, and trying to maximize the CPU compute power. So this is all about the CPUs. Then we move on to accelerators. Uh, until recently, let us say, accelerators were not very popular. We always relied completely on the CPU power, and but only in 2010 there were accelerators which were well known, or rather the Nvidia GPUs, which most of us know right now, started coming into the picture for the supercomputing field. Okay, so till then, why was it like all of a sudden these GPUs came in? No, before that they were used in the gaming world for getting better rendering. That's when it was analyzed that when you're doing this rendering, what is that you're doing? You're crunching floating point operations. So they thought, why not use this into the supercomputers? Because what does supercomputer applications do? They're crunching floating point operations, right? For you're using their applications and data. So that's how these GPGPUs, instead of GPUs, which were used in your video games or gaming industry, when it was brought in for the compute, it was known as general purpose graphics process unit, GPGPUs. And it all started in 2010 when it was added to the first China machine, which was called as Tianyi 1A. And the performance was tremendous. They were able to get, that was the first machine which was able to get the first 1 petaflop kind of a uh, performance. Till then, we were stuck till 2010. Whole worldwide, they were stuck with the teraflop. They were unable to cross the mark of the teraflop and enter the petaflop machines. But by adding these accelerators, GPGPUs, they were able to get the speed of the petaflop. So is it only the GPGPUs what are available? No. There has been something called as FPGAs. Most of, if any of you are from the electronics background, will be very familiar with this. FPGA is also an accelerator which has been around from very long before even GPGPUs entered. So what are these field programmable gate arrays are used and can also be used as accelerator. These are computer chips which can be rewired every time before the task is executed. And the very famous companies of FPGA were Altera and Xilinx. And with the supercomputing and with the compute being concentrated between Intel and AMD, they have bought out, Altera was bought out by Intel and Xilinx was bought out by AMD. And how can you use these FPGAs? They are programmed using languages like your VHDL and Verilog. They're not your, what do you say, the traditional ASIC nodes. They're more, if you look at it, what is that this FPGA has? It has more of control, configurable logic blocks because of which you can rewire it every time before you execute, right? And these are not like the cores. These are configurable logic blocks and they work for as a very beautiful accelerators and have been used for multiple purposes. But as we all know, the most famous one is your GPGPU. And in fact, it was, though we have now AMD and Intel coming into this, working around for making their own GPGPUs, NVIDIA has established itself so well. When you say GPGPU, the first card or anything, the company which comes into our mind is NVIDIA, right? And most of our applications, if I'm not wrong, have already been what people call it as CUDAized, right? More before you complete your C code, Python code, or your Fortran code, the CUDA is added to it to make it work on the NVIDIA GPUs, right? So let's say this is the motherboard, right? And your NVIDIA GPU is sitting on the PCI slot of it, right? So this is how in a system or in a server, your GPUs will be sitting on at the PCI slot. And as I said, with the entering of accelerators, the confusion of what are the languages, what are the paradigms to use, the confusion started increasing. Till then, people used to just use C, at least in the supercomputing world, okay? They used Fortran or C, and they were happy parallelizing using threading, or across the nodes, they were using message passing techniques. But with these GPUs, they brought in their own programming language, like the CUDA, or the other method what NVIDIA also entertains is one using OpenACC, right? And with the AMD coming in, they brought in their own HIP programming, ROC programming. And now with Intel coming in, they brought in their programming called as OneAPI. So at the end now, along with your C, Python, C++, Fortran, you use these parallel paradigms like OpenMP or pthreads for running threading in a CPU. Then for running across your CPUs, across the different nodes and servers of your supercomputer, you use MPI or PGAS. And to run on these GPUs, you either use CUDA or OpenACC or OneAPI or ROCm, right? So these are the new programming difficulties which have cropped up since 2010. So coming back now, since we are talking about the architecture, let's look into what is this NVIDIA GPU does and what is its compute power. How was it able to give the break to the supercomputers to enter into a petaflop arena, right? So the current latest GPU of NVIDIA is known as Hopper, and I'm talking of H100. And this gives each of one such card can give you 60 teraflops of floating point. It's not FP64. When you say floating point, it is FP64, right? That is around 30 teraflops. So your FP32 can give a performance of 60 teraflops. And then next, when you say FP16, these are your AI floating point operations. If you say AI flops, right? So they become FP16. And it's able to get one such card in your machine can give you 1,000 teraflops, right? So how is it able to get this 1,000 teraflops? It uses something called as symmetric SMs, okay, symmetric multiprocessors. In one card, it houses something like 144 SMs. And those SMs internally together, these 144 will make up something like 14,000 CUDA cores. So automatically, when you have CUDA cores of the size of 14,000 in this one card, you can get the performance of 1,000 teraflops of FP16 and 16 teraflops of FP32, right? So how is this hosted? If you look at it further, these green blocks, what you see, right? These are known as SMs. So each such SM, so there are something like 144 such SMs. If we blow up one SM, okay, this is how it will look. Each SM will have something like 32 FP32 units and 16 FP64, and again multiplied by 4 and multiplied by 144, giving you something like 14,000 CUDA cores, right? So this is the sheer number because of which it's able to crunch such huge numbers. Similarly, AMD is not left behind. They have also entered the GPU arena, and the terminologies used are a bit different. Okay, their machines are called as MI200, there's the MI series, and the performance of their card is something like 45.3 teraflops for FP64, vector FP64, right? When they say vector FP64, this is equivalent to your FP32, that is equivalent to your 60 teraflops of FP32, right? And when it's then when you have something called as matrix FP64, it is 90.5 teraflops. And total, there you saw they had something like 144 SMs. The equivalent of it in AMD, you can call it as compute units, CU, okay? And they have 256 such compute units. So NVIDIA H100 currently houses something like 144 SMs, and AMD GPUs equivalent to the SMs is called as compute units. They have something like 256 such compute units. So if you look at it, this is how these compute units are placed, or their patent comes in how they're placing their compute units or SMs, okay? How they're able to get their 256 compute units or 144 SMs or their 14,000 CUDA cores or their AMD something like 16,000 cores, AMD cores, what they have called. How are they placed within that particular card is what their patent is all about, giving different kind of performances of 45.3 or 60 teraflops or 90 teraflops. So what is that? It makes CPU and GPU different, right? So we know that they are all of the same size. The chips are all of the same size. How is that GPU is able to crunch so many or put in so many CUDA cores or your AMD cores into it? So this is how a typical, this is schematic diagram, okay, where you can say your CPU will have, let's say there's a quad core CPU where you have 4 ALUs, you have a control unit and a cache unit, right? In the same area, the GPU would place or rather reduce the control space and the cache space of that chip and rather utilize that space to overload it with the ALUs, okay, the compute cores, your CUDA cores, what we say. And these CUDA cores, when you look at these 4, all are symmetric, right? So it means they are synchronized across all the ALUs. Whereas when you look at these GPUs, how can you synchronize it? You can synchronize it only across the lanes, right? Because your control unit or cache unit is shared only across the CPU, CUDA cores across that particular lane only. So that is the reason you can say that GPUs are very good at running programs which are of type SIMD, we say, that is single instruction, multiple data kind of programs run the best on GPUs, because to run that you have multiple lanes cached out and control unit which is maintaining across it having 14,000 cores or 16,000 cores, right? But if your applications are not based on SIMD, that is single instruction, multiple data, then they have to be pushed onto your CPU. So your GPUs are good, they are fast for only a certain kind of programs only. But those are the kind of programs which are being used heavily for parallelization or most of the applications what we are seeing today. So that's how GPUs are very famous for crunching the SIMD applications. So till now we said, okay, so where is India ahead? This is what the world is going ahead. So this is a glimpse of what we want to show as this is the way ahead, what is planned and what is being proposed, where we are building our own CPUs, GPUs, and AI accelerators parallelly, not only the Param Rudra having our own servers, but also the chips. So which will be out by 2027. And our first machine using these completely Indian chips will be out in the market by 2027, hopefully. And then a pilot system is expected by around 2028 for it, and a mini exascale system of the same in 2028. Then we'd like to move on to something called as an hybrid version of this, or a SOC version, hybrid version of this indigenously developed chips to the boards, to the servers. And this is the plan for HPC, what we have, or rather the self-reliance into the chip industry to the supercomputing industry of India. Any questions before I move on to the memory architecture? Okay, about the processor building, any chance of CDAC designing such process in the future? Yes, sir, I have just shown you. We are in the process, or we are already in the process of building our own chips, nor our own processors, along with partners. And yes, that is a way ahead for self-reliance. If we cannot always depend on US, right? When you look at it, your Intel, AMD, NVIDIA, all are housed in USA. We cannot always depend on other countries to get our own processors. It will be the same as 1988, where at one day they'll realize they do not want to give that supercomputer to us. Maybe one day they'll realize we do not want to give the processor or the chips to you. So we need to be self-reliant. It shouldn't be like only when they impose sanction, we wake up and we take our time to build, right? So yes, we are working towards that goal. Any other questions? Okay, moving on to the memory architecture. Currently, typically there are only 3 kinds of memories what we are using in the supercomputers or any of your servers, right? What does that come to a servers? Once we have the best of the technologies which are put into a supercomputer, then those are downsized, and that's what comes in as a server down the lane, something like 2 years or 3 years. Today, if we are using socks like Intel Sapphire Rapid or something, so that Sapphire Rapid kind of a system will be downsized from 128 or 256 cores to the servers of 96 or something, and later on it'll again get downsized to your laptops with some smaller cores of maybe 24 cores. Right now we talk of in laptops something like 12 cores or something like that, right? So that'll increase or that'll cut down to something like 16 cores, 32 cores into your laptop down the lane. So that's how the processor technology has been handed over. That is, whatever is developed in the supercomputers 3 years ahead, that is what you get today in your laptops or your current single servers. So, and what are the memory options what we have in our supercomputers currently? We call it as either the distributed memory or the shared memory. In shared memory, we have something called as an UMA, that is uniform memory access. That is, within a socket, you have the same kind of memory which is visible to all the CPUs within that socket, right? That's the reason we call it as uniform memory access, because of this shared memory, or we can call it as an SMP based systems. Here the catch is all these processors need to be identical. They cannot be of different makes and versions, and that is when they'll have the equal access to the shared memory, and then they can, these CPUs can be called as cache coherent UMAs or cache coherent uniform memory accesses. So the contention with this is how many CPUs can you add into its socket, right? Currently, we have something like 24 CPUs, or max to max what we have seen are being used currently are 56 CPUs, okay, per socket. But how do we go beyond it? It is not possible using this shared memory. So that's where it's being used something called as a NUMA architecture, okay, the non-uniform memory access. When you have multiple sockets, right? Let's say in this particular picture, we have something like 8 socket machine, where each socket has, let's say, only 2 CPUs, right? So within this particular CPU, you have UMA kind of a memory architecture, but across, it's still shared, but for across, you'll be using or having a hop to this particular machine using the network or the interconnect, and then accessing the RAM or memory of this particular process. So that's why this is known as a non-uniform memory access, because not all the processors, if I need to access the region of the memory in this particular DRAM for this particular processor, it needs to jump, right? 1 to 2 hops before it reaches this particular memory region of the RAM and use that particular value in it. So that's the reason we call it as, here not all the processors have equal access time, provided if it is within the RAM region, then yes, it's not even a single hop, so it can access it. But if it has needs to access the shared memory across the sockets, it's going to take more time. So in this way, how many processors can we add? We can add, or what has been tried out as max to max, 1024 processors can be added this way. So processors directly are attached to this memory model, experiencing lower latencies. But for remote memory modules, yes, it's going to take some more time. That's the reason it's a non-unified memory access NUMA kind of an architecture. And the last, if it's not shared, what else do you have? Distributed memory architecture, right? If it's distributed, it's simple, like your lab systems, where each of your system will have its own memory. There's no shared memory concept at all. And for you to access, or your applications to access, they have to explicitly send it across using the message passing techniques to get the values from this particular different CPU, right, over the network. So this is the second kind of an architecture what we look at, that's a distributed memory architecture, where each has its own local memory, no concept of global address space or shared memory space. Here, data accesses between processors has to be taken care by the programmer by explicitly asking or explicitly sending messages to it for synchronization. Okay. Then moving on to, this is where your architecture in terms of your processors and memory end. Now we move on to parallel computing. Okay, so yes, you have the best of the best hardware, but you need to have the software or the technique, the parallelism, which is able to utilize these n number of cores, right? So that's where your parallel computing comes into picture. Usually, what is the kind of code what we all write? We write serial codes, right? Whether it's in your C, C++, Python, we just write serial codes. That is instruction by instruction, they are executed. So obviously it's a serial code, right? Let's compare this to this particular person who's trying to dig out a patch of land, right? Let's say this person is your CPU, and the patch of land what he is digging out is your data, right? That is, he's trying to crunch some data. So let's say if one CPU or one person takes 15 hours to dig out or to complete this set of data set, how much long will it take for 15 people, right? So when we say 15 people, how can you parallelize it? You would say 1 hour, right? But there can be parallel processing or parallelism which can be attained in two ways. That is, either by saving the time taken, that is, using the same data set, have 15 CPUs work on it and get the work done in 1 hour, or continue to use the CPUs for 15 hours, but you're going to crunch a bigger data set, right? That is, you solve larger problems. Both these kind of activity, you can say it as parallelism, where you're either saving time by employing more CPUs for the same data set, or you use more number of people, but you increase the data size and not rather save time, but rather you're trying to solve larger problems, right? Or crunch larger, bigger data sets. So where do you find this parallelism? As Sudarshan sir mentioned, parallelism is not just all about supercomputers. Even your handhelds, your mobiles also are capable of doing parallelism. Why? Even the smartphone, has 4 cores. So when you have 4 cores, you can parallelly work on them, or the applications can parallelly use those 4 cores, and parallelism can be achieved, right? So does that mean the parallel computing or parallelism is only up to your supercomputers? No, it is applicable on any kind of compute device which is being used today. Gone is the age where you had only a single CPU. Now when you have a hardware which is capable of giving more than one CPU, your technology or your parallelism or your parallel computing software or your application must be capable enough to utilize the complete infrastructure what's available. And when you say the infrastructure, I'm even mentioning your smartphones. But what is that we are writing till date? We teach right from our colleges only serial code. How serious are we about talking about parallelism or teaching parallelism? That has never been the way, or even we never think. That's the reason we say that parallelism is not about coding. It's more about you think parallel. That's when you can code parallel, right? Our thinking is serial. That's why we write our usual codes however we are writing. When our thinking or our algorithm is serial, how can we bring in parallelism? The parallelism has to be built in right from the algorithm level. Some terminologies what we interchangeably use here in parallelism, that is parallel processing, parallel programming, parallel computing. So are all the three same? No. When you say parallel processing, it is processing multiple tasks simultaneously on multiple processes. That is, you're actually executing the n number of tasks on some n number of CPUs. This is known as parallel processing. But the software methodology implemented for doing this parallel processing can be called as parallel programming. And what is parallel computing? When you utilize this technology of software methodology of parallel programming to run these tasks parallelly across multiple processors. That's when you can call it as parallel computing. So we can classify this parallel programming into, based on the data streams and instructions, as SISD, that is single instruction, single data, single instruction, multiple data. I've already talked about it during accelerators, right? This is the second kind of classification of the applications. Then multiple instruction, single data, and multiple instruction, multiple data. So where can we find these, or how do we say that these applications belong to this? Let's say the SISD. This was used in the UNIVAC era, right? Where you had each instruction being used, one instruction plus one data, what was being used. That is, you say load data onto this particular processing unit, then work on it, then load B, then you do instruction by instruction onto that particular data itself, single data, right? So it is single data with single instruction. So obviously in today's world, we do not use this SISD. Then we have the SIMD, that is, you have a single instruction, but the data is multiple, like your vectors, or which are being crunched. Most of your matrix and vector operations, they are of the kind single instruction, multiple data, right? The operation is the same, whether it's addition, multiplication, subtraction, but the data on which this operation is applied, that varies, right? So most of your SIMD operations, right, they are known as SIMD, operations of vectors or matrices, can be classified as SIMD operations. So which is the best kind of system which can work? The GPUs are the best to work on this single instruction, multiple data kind of programs. Then you have a third class of programs, that is the multiple instructions, single data. Where will you use multiple instructions for the same data? The best example is your cryptography algorithms, right? When you want to break your password, the password is a single, the instruction, the data is single, whereas the methodologies used to break that particular, to break in the password, what you're going to use, the different algorithms. So the instruction changes, right? So these are the next set of examples or programs, that is multiple instructions, single data. So this is an MISD kind of problem, and which is a kind of system which works best on it. Currently, FPGAs work the best on this MISD kind of data. Then last we have our MIMD, where you have multiple instruction, multiple data coming together to work on it. And obviously supercomputers are the best of, yes, your servers also, or the CPUs also work, but obviously the sheer number of CPUs what your supercomputers can provide is more, right? So we can say MIMD kind of operations are they work the best on your supercomputers. So moving on to the parallel programming design, I said, okay, we all think serially, we need to work on the algorithm in which we are working. So when we are creating algorithms for our application, that's when the parallelism has to be employed. So does that mean the current applications cannot be parallelized? No, that can also be worked on. How is it? Let's say you have a simple code, whether it's written in Python or C. We'll run profilers on it, right? These are tools what are available. You run different profilers on it. These profilers will be able to tell you the right place, or what we call it as a hotspot, where most amount of time is spent on your program. So you are going to pick out that particular spot or that particular part of your program and parallelize only that part of your problem, right? That's how parallelization is done incrementally on your current existing applications. Okay. So, and if you're not doing that, and if you're currently designing your algorithm, then this would be the method. We call it the PCAM. That is, you have a problem, you have the algorithm, but on that, first try to do the partition of it, then apply the communications involved, then agglomerate it, and then map it. So what is this PCAM method? PCAM is partitioning the computation of that particular algorithm, okay, to the smallest possible task which can execute independently. You're not going to be bothered about it requires some kind of communication, some kind of input from other instruction. Just partition the data currently to the smallest possible task which can execute independently. And then you do apply the next step would be communication. Now figure out among these tasks what you have, is there any amount of communication required? Are they exchanging data among themselves? Do they share the data among themselves? So once you determine that whether it's a global data exchange or it's at a local level, or what is the kind of data being exchanged within the different tasks, based on that you can agglomerate these tasks. If there are certain local tasks, that is some n number of small tasks in and around it are exchanging data, then we agglomerate, that is combine this task into a composite task. If it is global, then it makes no sense to agglomerate it, right? So next step is agglomeration of such tasks into a composite task. And once this composite tasks are created, now we need to identify how you're going to map it onto the CPUs or processors to work on it. That is, are you going to apply, like let's say I have some 6 composite tasks. Are you going to send it across to 6 CPUs which are just right next to each other? Or you're okay to send this task like on each node you have one CPUs available? Can you execute it on these different CPUs sitting on different servers? So this is the mapping what you have to work out on. Like how are they going to fit onto your processors, right? These tasks, how are we going to fit or attach to the particular process? That is the final step. Once this mapping PCAM method is used, then your algorithm is fit enough to run parallelly. Later on, while your algorithm is ready, now you can write your code in whichever language you want. It can be utilized. This is one way of doing, right? That's a PCAM method which can be utilized when you're designing your algorithm. But rather, if you already have existing programs, or even once your algorithm is in place, how do you write your code? You have like your C, C++, Fortran, Python. These are the languages what we have seen. Okay, so within a single machine, you want to utilize the cores within that machine. Then we use the shared memory concept, right? So we can do threading. And for threading, we use something called as OpenMP or pthreads. And in case if your machine or your data is so huge that it's able to spawn across different nodes, then how do you work? Within a single node, you can thread it, but across the node, you will have to use something called as an MPI, that is message passing interface mechanism is there. This is the MPI programming, what we say, to pass messages across the servers or across the nodes in the rack, and then you can pass across the values and start working on it. And within a server also, now you can use this threading concept for within the CPUs. Now if you have accelerator on that one server, then what is the language or the paradigm you'll have to use based on the make? You can use something like, if it's NVIDIA, you use CUDA or OpenACC. If it is AMD, you use HIP or ROCm. Similarly, these are the languages. Now, this is where things started getting complicated for the application developers. That is when now we are exploring, or the software industry is exploring something called as heterogeneous programming or sickle programming, where you have a single implementation and a single program, but you're not bothered whether you're running it on a CPU, across a node, across different GPUs. You must, all these things are considered as devices, and it just runs the same single program. It must be capable enough to run on a GPU having something like 14,000 cores, to a CPU having something like 64 or 128 cores, or a supercomputer having something like hundreds of nodes of that machine, right? So that is known as a SQL programming. This is something which is catching up nowadays with the application developers because of the node lock or vendor locks which is happening because of these different programming languages which are coming. That is, just imagine you are developing a program and today NVIDIA says we have the best GPUs, come to us, we will give you the CUDA codes, and they CUDA is your codes, and you are happy running on it. But the next, in a year or two, you have a next machine, an AMD machine. Currently, AMD machines are very powerful. You saw that, right? In the top 500, the AMD machines are quite powerful. But now the machine is there. But what about your application? Is it portable? No. Your particular application is stuck with CUDA. So now to run on AMD, you have to port your whole code to AMD to their particular language of ROCm or HIP, right? So next, let's say there's a third machine coming. So next you have to again port your application. So if the porting of your application is of some 100 lines of code, it's not a big deal. What if your application, most of our applications, what we are talking of, they are in millions of lines of code. It is a very huge effort that leads to, so people tend to not go for porting. So automatically people are stuck with the same NVIDIA GPU and the same Intel processor, because this is what they build their application for. Now the codes are not portable across, right? So to remove this vendor locking, there is an effort across all the sections of the HPC, or rather say the programming environment, to build something called as an heterogeneous code, something like SQL, right? Where you can write the code or application for any device. I'm just saying today it is the AMD device, tomorrow it is some ARM device, or today it is an NVIDIA device. The application is the same. So porting, the problem of porting the application or device locking is avoided using this SQL programming or heterogeneous programming. So let's look into one example before winding down. This is a vector addition. Okay, this is your serial code. Leave the green part of the code. This is your simple serial code, right? Where you're adding two vectors and you're getting the third vector of based on addition. Now, how do you parallelize it? I said you can, within a server, you can apply OpenMP or threading, right? So this is a directive based parallelism where you apply or you find out the ideal area which needs to be parallelized. So obviously in this whole code, A of I plus B of I is the most time spent kind of a line of code on this particular program, right? So you apply parallelism there, hash pragma OMP parallel and hash pragma OMP for, and these two lines of code is good enough to start your parallelization for this, right? And while compiling using GCC, you add the flag -f OpenMP with ICC -OpenMP and with PGCC compiler -MP, and your executable is ready to run on the 10 cores or 48 cores of the single node using OpenMP. Okay, and now I said, if I want to run across nodes, right, that is across machines, then you need to use something called as an MPI, explicit message passing instruction, right? Now with the same example of vector addition, what we have, right? Here I'm just using a different variable, AP of I plus BP of I giving CP of I, right? But for running across this, we initiate the MPI program. All the green lines, what is written, right? This is the MPI program. If you leave this, the rest of the black line of your code is your serial vector addition, right? So you scatter the number of cores, like let's say the value of n is something like 1000. So 1000 divided by some 32 systems you want to run it across, divided by 32 and scatter those values across the 32 CPU, 32 systems, and then do the addition and get the local addition of that particular vector, and then bring that back to the master node using MPI gather, and then in that particular master node will print out the value of this whole vector addition. Okay, this is using MPI. Now, if I want to use NVIDIA accelerator, I need to use something called as an OpenACC. For the same vector addition, I'm going to apply hash pragma ACC instead of OMP, what you saw for the CPUs, what we're using, threading for CPUs. For GPUs, you can say ACC. Then each of this, it's known as a kernel. You copy the data into the GPU and out of the GPU. So you need to say what is the variable you're going to copy in and what is the variable or the vector what you're going to copy out. And based on this, now you have identified the area which is going to run parallelly on a GPU, right? And you're supposed to run it using the compiler called PGCC using -ACC. So this will run on your NVIDIA accelerator. Then the last example is your heterogeneous programming. Here for us, either you use ICPX-FSQL or this ParaCC with the program name based on the device available on that particular program or your machine. It will run on those devices and it will come back. Whether it is just the CPUs or if it has an NVIDIA GPU or it has an AMD GPU, it will run on it and utilize all the cores possible and the result will be brought back. Okay, this is your secular heterogeneous programming where your CPUs, GPUs all are considered as devices. And again, the program is the same, vector addition. Here you're just going to allocate using malloc share and you have a queue which is being used for identifying the device. And then you call that particular queue with parallel for as the kernel and then do the vector addition. So this is your heterogeneous programming using SQL. So these are some of the parallel paradigms or ways of running the existing codes or your algorithms what you have developed. How do you parallelize or run along with it? Any doubts still here? I'll just have another 5 to 10 minutes. Okay, no doubts. Then we move on to use cases. I guess this has been a major question. Yes, supercomputers are superb. You have servers with so many CPUs. You're using parallelism. But what is the code? What is the applications which are running, right? If you look at it, you can find application in every domain area. Obviously, including India, we started using supercomputers for weather prediction or forecasting. To the date till now, we look at it, we can say the weather prediction is quite accurate now, right? It doesn't rain. Like if the prediction is of rain is today, we do find the rain coming today itself, right? And we are able to even say the weather with the weather prediction at what time of the day it will rain in this area, right? So that is the precision what we have achieved. And this kind of predictions has been possible using supercomputers. Then challenges with material science, that is what are the different kinds of materials that can be used. Like there is a system called Lumi, okay, where they're doing study on different kinds of materials for production for green hydrogen. Okay, what are the materials that can be used? So it doesn't mean that you have to actually work it out in the lab. You can simulate or you can prototype using your applications to find out the most suitable materials. And once there is a success using this particular application or the prototype, yes, this is the kind of materials that can be used to create your work, then you can actually go to your lab to actually create it, right? Or when you look at the semiconductor design, you do not make your one ASIC design, it's said to take around 2 years. It doesn't mean you have to wait till 2 years to know whether your design is a failure or a success. You can actually prototype or you can simulate it on your system, on your supercomputer, and run it and know whether this particular design will work or not. Similarly, the designing of drugs, right? One best example, what I have seen in my journey was the developing of malaria tablets using the Garuda grid, which was working in India in somewhere around 2005 to 2012, okay, where these supercomputers were used for developing the malaria tablets. Or rather you can even the first human genome which was calculated, biologists would know the ACTGs that has been identified, right? The whole human genome. How was it identified? By using the supercomputers. Or if you're going to say the challenges of transportation can be simulated and you can figure it out. Or the nuclear fission, right? You need not actually work on it. You can do a simulation and figure out whether it will work or not. And if you look at exploration of oil and gas, like ONGC today uses supercomputers to dig out places where they can find the required oil and gas. It's not like today they realized, okay, there might be a place where I would like to dig in and they would go around doing the actual oil drilling. No, they do run these simulations and to find the composition of the rocks or the different materials what's required. If those composition matches using these simulations, that's when they decide, okay, this is the possible place for getting the required oil or gas, and that's when they go in for the actual work, right? So you have an obviously visualization and graphics. These are some things which have been there for are best, like when you use GPUs, right? So there are, when you look at it, every domain has its application which requires supercomputer to fasten the process and get your work. The best example would be development of the COVID vaccines, right? It was not like it was all done in a lab. Obviously, people have employed supercomputers to run on it, whether these vaccines or these combinations or the ribosome-based vaccines when they were developed, do they work or not? Then based on those analysis and the simulations, that's when the actual tests were done to develop those drugs. So before ending, I would like to play this video. Are you able to hear the audio? Can I play it?
Yes,
Yeah,
ma'am.
yes, we can.
Okay.
From decoding the secrets of the cosmos to driving revolutionary advances in medicine, agriculture, climate sciences, and energy management, India's supercomputers journey represent the pinnacle of technological innovation, propelling us into the new paths of modern progress. Under the leadership of Honorable Prime Minister Shri Narendra Modi, the National Supercomputing Mission is being jointly steered by MITI and DST, executed by CDAC and IISc, carrying forward the legacy of Atmanirbhar Bharat under Phase 3 of NSM.
सुपर कंप्यूटिंग सेंटर परम शिवाय की शुरुआत से नेशनल सुपर कंप्यूटिंग मिशन को गति मिलेगी.
CDAC is establishing Param Rudra, state-of-the-art supercomputing systems across the country. These systems are based on Rudra servers, designed, developed and manufactured in India. CDAC has deployed a 3 petaflop supercomputing system at Inter-University Accelerator Center, Delhi with 650 Rudra servers. This facility will support research in medical treatments, energy production, environmental monitoring, and many other related domains, and facilitate researchers of more than 350 universities and institutions under IUAC. The Giant Meter Wave Radio Telescope GMRT in Maharashtra, operated by the National Center for Radio Astrophysics NCRA, is one of the world's largest and most sensitive radio telescopes. CDAC has commissioned a 1 petaflop Param Rudra supercomputing system equipped with GPUs enhancing GMRT's sensitivity to low and mid radio frequencies, enabling advanced studies in radio astronomy and the interstellar medium. An 838 teraflops Param Rudra supercomputer at SN Bose National Center of Basic Sciences, Kolkata features 180 Rudra servers, facilitating researchers to address complex problems like material science, earth science, high energy physics, cosmology, and astrophysics. It also serves a broad range range of users from various premier research institutes in and around Kolkata. These three Param Rudra facilities are powered by CDAC's system software stack, providing easy provisioning, advanced real-time monitoring and management. This commences a new chapter towards self-reliance in high-performance computing, ultimately leading to exascale. Supercomputers used for advanced research and data analytics can significantly impact the agricultural sector. By leveraging these powerful NSM systems, researchers can develop advanced seeds, improve fertilizers, and enhance soil quality. Supercomputing also enables more accurate weather forecasting, helping farmers make informed decisions. These advancements ultimately boost crop yields, optimize resource usage, and increase farmers' incomes, driving growth and sustainability in agriculture. India has pole vaulted in HPC technologies. This is the journey of India's supercomputers, a story of innovation, resilience, and a future filled with limitless possibilities in solving grand challenge problems, thereby enhancing the quality of research for the benefit of mankind. NSM proudly announces the launch of its first in the series of indigenously designed, developed and manufactured in India supercomputers. Rudra, Hamara Sankalp, Atmanirbhar Bharat, Vikasit Bharat.
I think this video has given you an idea of the different kind of applications or what can be used or what we are currently using. It's not that these applications, what we intend to use in India are for the future. These are the applications what we are currently using on the systems. It's not something there are being used only in the outside of the foreign countries, but we are utilizing our supercomputers for our own applications, right from your agriculture to disaster managements for your forest fires. So this is the use cases what people when you asked for, like I thought there can be nothing better than showing this particular video which talks about the different kinds of use cases what in India we are using. And we talked about only the 3 systems. We have 15 such systems which are being used. And let me say these systems are being used at 90% of its systems are being utilized at 90% continuously, right? So you can understand the kind of work which is going on and applications what I've shown you the range of applications what can be used it can be used for. Now other than this, there are some links which I'm leaving up with you for the worldwide some of the supercomputers what they are using for, and in India what the same YouTube short video. And there's one more video what I found about NCRMW